Hi, AP Physics students. This is Mr. Evely coming to you, not live, from Granville High School. We're doing electric fields right now, and for whatever reason, we can't be in the classroom, probably weather related. The next topic we need to talk about in the realm of electric fields is the electric field of an array of charges. So far we've dealt with a single charge. So if you have a charged object, it creates an electric field in all directions. If I want to know what the electric field is, like right there, I need to put a tiny charge right there, usually a tiny positive charge known as a test charge. I say, okay, what's the force on the test charge? What is the magnitude of the test charge? Take the ratio and you have the electric field. Without knowing the magnitude of the test charge, just knowing how big this guy is, let's say we call him Q, and knowing the distance between Q and the point where I want to find the electric field, I'm going to have to do a little bit more work. I'm going to say if the test charge, baby Q, is located right there, then the force between him and this big charge here is going to be K little q big Q over R squared. So in other words, in place of F, I put this guy and divide by the baby charge, the test charge. So for a single charge, the electric field nearby is equal to K Q over R squared, where big Q is the charge creating the field, R is how far away you are from it. What if, however, you have a line of charge, a whole bunch of charges, say, on a string, that goes a long way this way and a long way down, and I want to find the electric field right there. What I basically have to do is deal with the fact that all of these segments of the string are single charges and add up the effect of all those single charges on this spot. So in other words, like Miss Stoughton would, I'm going to break this up into a bunch of little segments, call that R, figure out what E is right there, and add up all those E's from maybe infinity this way to infinity this way, and we can find out what the field strength is due to this long line of charge. Okay, we actually have a really easy way of doing that in the next chapter, so I'm not going to derive that for you. But when you're dealing with a long line of charge, you have to deal with something called length density. So the charge distribution, lambda, means how many coulombs of charge per unit length. Okay? You could also, if you're dealing with calculus, say dq dl. In other words, if I take a tiny little bit of this length, dl, little tiny bit of charge on him, dq, that this ratio of charge to length, if I take a tiny length of this string, should be equal to all of the charge divided by all of the length. So suppose this string is not infinitely long, but is just very, 3 meters long. The total charge divided by the total length would be the charge density. Now this would be true only if the charge density is uniform throughout. Okay. We could also have an area of charge. So I could have a sheet of charge where we put charges uniformly distributed along this sheet. And I could say, what is the strength of the electric field right here, a certain distance above the sheet? For that we use sigma. So that's charge per unit area, or dQdA. So take a certain area of that sheet, figure out how much charge is on it, find the ratio of charge to area. It's called sigma. So lambda is length density, and sigma is area density. The last one is rho, which is charge per unit volume, or dq dv. So imagine I've got a sphere. Throughout that sphere I have charge. Okay, I could say that there's a certain amount of charge per unit volume. Or I take a little teeny tiny piece of that volume and it's got a certain amount of charge. If the charge density is uniform, every little tiny bit of volume of this guy will have an amount of charge so that the ratio of charge to volume is constant, if it has a constant density. If it doesn't have a constant density, then rho may have an equation related to it. But we're going to say lambda is charge per unit length, sigma, charge per unit area, rho, the Greek letter rho, charge per unit volume. Okay? So 3 symbols you should know. Now, one arrangement of charge that is not susceptible to the magic method we're going to come up with next unit is a ring of charge. So imagine that we've got a ring. Let's say it's a perfect circle. It's very, very thin, made up of positive charges. Okay? If you want to know what the field strength is at the very center, imagine putting a positive test charge there, and all of these guys, uniformly distributed around the outside, are going to repel him. So the field right there at the center of the ring is 0. Well, that's not very interesting. So what we're going to do is we're going to look at this ring kind of in perspective. Okay, it's still the very same ring. We're just kind of looking at it off to the side. Okay, let's say it's got a total charge Q on the entire ring. From the center, we'll go up to some point, distance Z from the center of the ring. And we'll say, okay, what's the strength of the field? Right there. Now, that's a tougher question. The strength of the field is not going to be 0. If we put a positive charge here, it would probably suggest that that positive charge is repelled by the ring because the ring is positively charged as well. To figure out the strength of the E field, we're going to perform the same thing I mentioned earlier. We're going to take this, break it up into tiny pieces. Each little piece I'm going to call ds. dl works too. The charge on every little piece I'm going to call dq. The distance from this little piece, from here to that point up here, is r. The radius of our ring, we're going to call capital R. Okay, so we've got a right triangle here. This angle theta is going to be important later. What we're going to do is we're going to figure out the effect of this little bit of charge on that point. So this little tiny bit of charge, not the entire ring, just him at that point, is going to create an E field in that direction. Okay, call it dE because it's one portion of the entire field. Then what we're going to do is add up the effect of all of these little segments all the way around the circle. So this is going to require a little bit of calculus. Okay? So what we're going to do is add up all these guys, but you imagine adding up these guys as we go around the circle is going to be a cone of dEs. We're going to have to add up the effect of all these fields in like a cone. Okay, well, there's an easier way. If I take this dE and break it down into 2 components, okay, here's my theta. This guy is dE sine of theta. This guy is dE cosine theta, okay, pointing straight up. When I go around the circle and add up the effects of each one of these charges, dE sine theta goes all the way around. in effect, dE sine theta is going to cancel itself out as I go around the entire circle. dE cosine theta, I just keep adding those guys up, and they all point, in the up direction, in the positive z direction, which kind of makes sense because if I put a positive test charge there, you kind of expect him to get pushed away from the center of the ring. So I'm going to say E is going to be the summation of all my dE cosine thetas. Okay? I'm going to take all those guys, add them up as I go around the circle. All right. Now, the effect of this little guy on here, that is the strength of dE, is going to be derived from this guy here. It's basically a point charge, kq over r. So I'm going to say, instead of kq over r, I'm going to say k dq over r, that's r squared. All right? Times the cosine of theta. So here's the field due to a single point charge, just this little tiny bit of the circle, times the cosine of theta, because I only want that component. I'm going to add them all up. That's what the S means, the integral sign means. I'm going to add up all of these guys all the way around. All right? Now, I'm going to make a couple of changes to this equation before I finish it. What I'd like to do is add up the effect of all the charges here from S equals 0 to S equals 2 pi r. That is, all the way around the entire circumference. Okay? That means I need to make some changes. I'm going to change dq because lambda, I think if you can still see that, yep. Lambda is dq ds. Okay? It is the total charge on the ring divided by the total circumference of the ring. That's going to be 2 pi r. But I could say then that dq is equal to lambda ds. Now, changing that variable is going to allow me to say I want this from s equals 0 to s equals 2 pi r. That'll allow me to add up the effect of all these guys around the circumference. Another thing I'm going to do, r, if you take a look at my triangle here, r is just the square root of big R squared plus z squared. Okay? The cosine of theta, if you take a look at my triangle, is adjacent over hypotenuse. Cosine of theta is z over r, or z over the square root of r squared plus z squared. So I'm going to make all these changes at once. Okay, I'm going to replace the r here with this, so this guy gets squared. But then he also has to be in the denominator. I'm going to have a z in the numerator, and I'm going to change dq to lambda ds. So I'm going to do this all at once. So get ready. Here we go. Sorry, that's 0 to 2 pi r. Okay, and I still have the k. dq becomes lambda ds. Cosine theta, I've got a z on top, and I've got this times this times this. In other words, I've got r squared and an r here, so basically I've got r squared plus z squared to the 3/2 power. Okay? So here we go. We need to take an integral from 0 to 2 pi r. Now, here's the beauty of this. Once we've made all these changes, the integral becomes really easy. Because remember, Ms. Stoughton's going to teach you that any constant in the integration can be taken out. So I can take out of this integration k because it's a constant. Lambda, if it's a uniform distribution of charge, lambda is a constant. Z is a constant for this particular problem. We're keeping Z a certain distance above the ring. R squared plus Z squared is all constant, and that's to the 3/2. The only thing left inside the integral is ds, and we're going to integrate it from 0 to 2 pi r. Now when you integrate ds between 0 and 2 pi r, the integration of ds is s. Then we're going to replace it with this minus this. So all of this just becomes 2 pi r. So here we go. E is equal to k lambda z times 2 pi r all over r squared plus z squared to the 3/2. You say, wow, okay, that is the electric field right there due to this ring of charge. Crazy derivation. Now, what's kind of cool is that this piece right here is the length density times the length of the ring. Wait a second. We said before that the length density is the total charge divided by the total length. Therefore, lambda times 2 pi r is just big Q. It's just the charge of the ring. So, make this a little simpler looking. We're going to say it's K Z Q over r squared plus z squared to the 3/2. Okay? That's a ring of charge. Z is the distance above. R is the radius of the ring. Total charge on the ring is Q. There's the equation for the electric field at that point right there. Okay? Now, a couple things we can do to see if our equation is right. Check out the extremes. For example, what if we let z equal 0? Okay, so we drop this down, 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 let z equal to 0. What's the answer? Well, if we have a 0 on top and a 0 right here, the answer is 0. It's what we expect. E is 0 at the very center of the ring. Okay, that works. What if z were really, 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 really big? What if we went off the page, off into the auditorium or into Wyoming, and we say, okay, let z be really, 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 really big compared to r. Okay? If that happens, z gets really big and matters a lot. R doesn't matter so much. Okay? So if we do this, we say, oh, okay, that's like having a z cubed on the bottom, which cancels out one of our z's, which means we've got k q over z squared. Oh, that looks familiar. KQ over r squared is for a dot. In other words, when we let z get really big, this ring starts looking like a dot. If you see that ring from far away, it just looks like a dot of positive charge instead of a ring of positive charge. So letting z get really, really, really big means, hey, it starts to look like a dot. Let z get really, really small, and you get 0 because you're in the center of the ring. Okay, so the equation kind of makes sense. It kind of works. All right, quick example using rings that you may see as you do the problem set. They love stuff like this. Okay, we've got two concentric rings of radius big R and a radius of big R prime, just to make them look different. Big R prime is 3 times the size of the smaller radius. Point P lies a distance d, so notice they're using d instead of z. Oh no. A distance of 2r away from the center of the small ring and the big ring. The small ring is uniformly distributed charge of positive q. So this is a bunch of positive charges uniformly distributed in a circle. Charge q. Okay. What's the charge on the big ring? so that the E field right there is equal to 0. You say, wait, well, the positive charge here on this ring is going to make an electric field straight up, positive Z direction. What could cancel that out? That would be another field in the negative Z direction, pointing downward. That's got to be set up by this guy then. So we reason that this guy must be uniformly negative. So the question is, okay, how much negative charge do we need on this big ring in order to cancel out the effect of the positive charge on this ring right there? Not anywhere, but right there. So one thing that we could do is say, okay, if these two guys cancel out, then the magnitude of the electric field they create there must be 0. In other words, the inner ring is creating an electric field that way, and the outer ring is creating an electric field that way, and they just have to be equal and opposite. Okay? So what if we set E1 equal to E2? All right? I'll slap absolute value signs on them to make you happy because, yes, they are in opposite directions, so they're not equal. They're equal and opposite. And let's go for it, and let's see if we can figure out what the charge is, call it Q prime, on the bigger ring. So the electric field due to the inner ring is got to be K, D, Q. Okay, we're using D instead of Z because, you know, that's what we're doing. All over R squared plus D squared to the 3/2 power. Okay. The other guy is K, D, Q prime, R prime squared plus D squared to the 3/2 power. Okay? Now, a couple of things. They're telling us that D is equal to 2R. That's going to simplify things. They're telling us that R prime is equal to 3R. That'll simplify things too. So let's make those changes and see if we can solve the problem. By the way, I think we can probably lose some stuff here. Okay, on either side of the equation. On top of here, I've got Q. On the bottom, I'm going to have R squared plus 2R squared to the 3/2. Okay, all I did was replace D with 2R. On the other side, I've got Q prime. I've got R prime, so he's 3R squared plus 2R squared to the 3/2 power. Okay, you can already see where this is going. This is going to be 4R squared plus 1. This is 5R squared on the bottom. Okay, over here I've got 9R squared plus 4R squared. So he's going to be 13R squared to the 3/2 on the bottom and a Q prime on top. All right, let's separate this out. I've got Q on top. I've got 5 to the 3/2 power here. I've got R squared. If I take the square root, I'll have just R raised to the 3rd power here. Over on the other side, I've got 13 to the 3/2 power. And again, taking the square root of R squared leaves me R, so I've just got R cubed here and a Q prime on top. Oh, look, we can lose the R cubes. All right, so it looks like that Q prime, the magnitude of Q prime that is equal to 13/5 to the 3/2 power times Q. Now, of course, we also know that it's a negative charge. So the way we set it up as absolute values, we have to remember that the large ring had a negative charge. All right, so if we were to punch that baby out, we would get something like negative 4.19 Q. All right, so again, using the equation we now have for the electric field due to the presence of a ring distribution of charge, we can figure out what the electric field would have to be at a certain place. We can figure out what the charge on a ring would have to be to have a certain result at that point. Just becomes algebra once we have the physics. Okay? All right.